Welcome to the Explainer. We're jumping right in today because we are tackling one of the most puzzling, everyday mysteries of the winter season. So have you ever noticed that right after the winter solstice, the official shortest day of the year, passes, the days are technically supposed to be getting longer. But your mornings? They remain completely pitch black and absolutely freezing. Honestly, it feels like a glitch in the matrix. Well, today, we're unraveling this bizarre phenomenon. I like to call it the solstice paradox. We are going to look at the invisible astronomical gears turning way up above our heads to understand exactly why our clocks, our sunrises, and our seasons seem to get temporarily totally out of sync.
Okay, let's dive into this, because this is a frustration we all feel, right? You mark June 21st on your calendar. You celebrate making it through the absolute shortest, darkest day of the year, in the Southern Hemisphere. From tomorrow on, the days are getting longer. We start gaining those precious minutes of sunlight. Yet, your alarm goes off at 7 a.m. a whole week later, and there is no way around it. It is still completely dark outside. So, why does the sun continue to rise later and later, even after the solstice is already behind us? To understand this really frustrating lag, we first need to quickly ground ourselves in the mechanics of our solar system.
Let's just start with the baseline science. Our seasons and the solstices themselves are caused entirely by the tilt of Earth's axis. As our planet makes its yearly journey around the sun, the poles are either tilted directly toward that giant ball of fire or they're leaning away from it. During the southern winter, the southern hemisphere is pointed away from the sun. This means the sun reaches its most northerly point in the sky around June 21st, and it appears much lower on the horizon for anyone living in the south. The direct result of that? Well, you get less time in the sunlight each day and significantly colder, more wintry weather, while the northern hemisphere is pointed toward the sun and soaking up all that heat. To really put into perspective just how dramatic this axial tilt gets for the southern extremes, think about this specific number: 9 hours and 1 minute. That is the total amount of daylight the city of Hobart gets on the actual day of the winter solstice. Out of a 24-hour day, they are spending almost 15 hours entirely in the dark. It is this tiny, fleeting window of sunlight that profoundly impacts daily life and the local climate. And this brilliantly illustrates the divide. Up north in Darwin, you're still getting a relatively robust 11 hours and 24 minutes of daylight on the shortest day of the year. But as you travel further south toward the pole, that sunlight literally drops off a cliff, all the way down to Hobart's 9 hours and 1 minute. It's just simple geometry. The closer you are to the poles, the less sunlight you see during the winter solstice. Now, if Earth's orbit was a perfect circle, this would absolutely be the end of the story. Our earliest sunset and our latest sunrise would both happen exactly on this same day.
But of course, the universe is rarely that simple. Astrophysicist Professor Jonty Horner from the University of Southern Queensland sums it up perfectly when he says, "But there's an extra thing going on." And this is where our scientific mystery really takes a fascinating turn. We have to pivot our narrative away from the obvious axial tilt that we all learned about in grade school and introduce the astronomical plot twist that is secretly messing with your morning alarm clock. That extra thing Professor Horner is talking about? It's the actual shape of Earth's orbit. It is not a perfect, symmetrical circle. It's actually a slightly squished, elongated shape, what scientists call an ellipse. Now, really quickly, we need to debunk a very common misconception here. This squished shape does not cause our seasons. Our changing distance from the sun over the year doesn't dictate whether it's winter or summer. The tilt does that. However, this squished orbit does have a highly specific, hidden influence on the exact timing of our sunrises and sunsets. Because our orbit is an ellipse, our physical distance from the sun changes throughout the year. We're actually closest to the star in early January, and we're furthest from the sun in early July. Now, according to the laws of physics, specifically Kepler's laws of planetary motion, when a planet is closer to its star, the gravitational pull makes it move faster along its orbital path. When it's further away, it moves slower. So right near the winter solstice in late June and early July, our planet is physically moving slower in its orbit around the sun.
To understand why this slower orbital speed matters to your mornings, we need to define a really crucial astronomical concept: solar noon. Solar noon is the exact, precise moment when the sun reaches its highest point in the sky and appears directly above our heads. It's the literal, physical midpoint of the day based entirely on the sun's position. This happens completely independently of whatever the rigid mechanical clocks on our walls or the digital clocks on our phones happen to insist the time is.
So, the crucial point is this. Because the Earth is moving at varying speeds in its orbit, it doesn't always take exactly 24 hours for the sun to return to solar noon from one day to the next. The Earth's rotation on its own axis is incredibly constant, yes. But because it has moved a slightly different distance along its orbit each day, it has to rotate just a tiny bit extra or a tiny bit less for the sun to appear directly overhead again. This variance creates a tiny daily offset. It basically means true solar time and our rigid, perfectly 24-hour human clocks are constantly drifting slightly out of sync. Because our 24-hour clocks don't perfectly match the true solar time, the timing of sunrise and sunset gets shifted. If you map it out chronologically, it's like a bizarre timeline. Step 1. The earliest sunset of the entire year actually happens well before the winter solstice. Step 2. The winter solstice arrives, bringing the shortest total amount of daylight. And then step 3. The latest sunrise of the year doesn't happen until a week or more after the solstice. The darkest mornings and the earliest dark evenings are totally disconnected from the actual shortest day of the year. As Professor Horner explains, it means the date of the earliest sunset and the date of the latest sunrise are offset. I really want to emphasize this because it's such a brilliant realization. The movement of the Earth speeding up and slowing down in its orbit is happening completely separately from the change in the length of the day caused by the axial tilt. These two separate cosmic cycles are overlapping, creating this incredibly confusing offset effect where the mornings stay dark even as your afternoons finally start getting lighter. Now, what's really interesting about this slide is seeing how this offset actually plays out in reality across different latitudes. Look at how drastically different these dates are depending on where you live in Australia. Up in Darwin, the earliest sunset is all the way back in late May, and the latest sunrise isn't until mid-July. But as you move further south, from Brisbane to Sydney, right down to Hobart, those dates start squeezing closer and closer to the actual June 21st solstice. When we summarize that data, we see a massive contrast. Up north, in Darwin, the offset is roughly 3 whole weeks before and after the solstice. That means, for weeks, your mornings are actually getting darker while your evenings are simultaneously getting lighter. But all the way down south in Hobart, that whole sequence happens within a tightly packed single week. So, why does the timing of this offset shrink so dramatically the further south you go? The answer lies in the sheer power of the changing seasons at the poles. Professor Horner states, the nearer to the equator you are, the less the length of the day changes. Up near the equator in Darwin, the total amount of daylight doesn't shift that drastically, so that small, subtle effect of Earth's slow, squished orbit becomes very visible, and it shifts the sunrise times by weeks. But down in Hobart, the length of the day is changing so drastically and rapidly around the solstice that it completely overwhelms and drowns out that tiny orbital effect. That rapid gain in daylight forces the latest sunrise much closer to the solstice date. So, let's see how all this builds into your chilly morning reality. The great news is, the days are finally getting longer. The latest sunrises are passing and your mornings will start getting brighter, but don't pack away your heavy coats just yet. Because of the way Earth's oceans and land masses slowly release heat, there's a thermal lag. Even though we are gaining sunlight, you can expect temperatures to actually keep dropping for the next few months. Yep, the absolute coldest weather of the year is actually still ahead of us. So the next time you wake up freezing in the dark and you check the time on your perfectly programmed digital phone, I want you to remember that your watch doesn't control the universe. We are literally riding on a tilted, squished, slightly wobbly rock hurtling around a star at varying speeds. It makes you wonder, right? What other invisible cosmic forces are out there, secretly messing with your daily routine? Thank you so much for exploring the solstice paradox with me today in this explainer, and remember to keep looking up.